Let's apply this scenario concept to the railway sector. In this way, we can identify decarbonization opportunities and explore how different scenarios analysis approaches can help us analyze these possibilities effectively. As we discussed earlier, in this course, three main options have been identified as potential opportunities for decarbonizing the railway sector. Let's explore which scenario analysis category can fall into and how we can leverage the modeling tools presented in this course to outline future decarbonization pathways for the railway sector. The introduction of the energy community framework can enable the exploitation of decentralized renewable energy potential. This perspective can be effectively addressed using the possible scenario approach. The regulatory framework for energy communities is already established in Italy, and the necessary technologies are widely available in the market. The advantage of using the proposed approach and the modeling tools presented in this course lies in the fact that geolocalized energy demand estimation allows for demand-supply optimization from the perspective of an energy community. Modal shift scenario. This scenario evaluates how the railway sector can act as an enabler for decarbonization pathways across the entire transportation sector. The modeling approach and the tools presented in this course can help estimate the evolution of railway energy demand at sectoral level under the assumption of a partial shift of current services, passenger and freights, from road to rail. This analysis fits with the probable scenario category. Since modal shift for transport is a feasible option, although a dedicated regulatory framework to incentivize this change is currently lacking. It would be beneficial to analyze the impact of such policies on the Italian energy system to inform the decision-making and policy development processes. Alternatives to internal combustion engines for non-electrified lines. This approach fits well with the preferable scenario category. To achieve the decarbonization target for the entire Italian railway sector, it is crucial to identify alternatives that can eliminate the use of diesel and heavy fuels for non-electrified lines. Potential alternatives include hydrogen fuel cells and battery-powered trains. However, these technologies are not yet widely economically available on the market. The proposed approach and the modeling tools presented in this course can be instrumental in this context. Specifically, detailed route information for non-electrified areas for the sector allows for precising optimization and feasibility assessment of alternatives to internal combustion engines, such as hydrogen hybrid trains. By conducting scenario analysis in this way, we can explore comprehensively different pathways to decarbonize the rail sector, each with its specific set of challenges and potential solutions. The goal is to utilize the modeling tool and the method discussed in this course to guide strategic decision, inform policy development, and ultimately create a more sustainable and energy-efficient railway system. In summary, leveraging scenario analysis helps us understand future possibility, scan for potential changes, build consensus for change, and manage risk. By distinguishing between probable, possible, and preferable scenarios, we can better navigate the complexities of decarbonization in the rail sector and make informed decisions that contribute to a greener and more sustainable transportation infrastructure. To conclude the course, we would like to focus on 5 recommendations for modelers that are endorsed by major international agencies active in the energy modeling field: EIA, IRENA, World Bank with ESMAT program, and similar. These recommendations are: support country-led energy planning processes that work in partnership with key stakeholders. These should achieve broad consensus on strategic goals and plans, help to empower the relevant authorities at national and regional level, and also at the subnational level, to really implement the plan and push back on proposals that do not align with it. Coherence and inclusivity. Support governments to ensure that strategic decisions taken in the energy sector are coherent with broader economic, social, and environmental goals, including sustainable development goals and nationally determined contribution under the Paris Climate Change Agreement. By committing to evidence-based, integrated, and inclusive energy planning processes that lead to fair and technically sound energy development programs. Capacity building. Support governments in the definition of priority capacity building activities which strengthen the capability of the national institution to take the lead on strategic energy planning. Incorporate plans and evidence into decision-making and implementation processes. Commit coordinating development partners in line with the government's vision. Request for support and goals. Avoid fragmentation and duplication of efforts. Robustness. Promote the use of models, analysis, and decision support tools that, first, have a strong technical and economic foundation. Second, are fit for purpose to deal with rapidly changing circumstances in the energy sector. Third, are able to support flexible and adaptive approaches to the energy sector planning that can be easily and regularly updated. Transparency and accessibility. Promote open access to modeling tools and results. Encourage peer review of modeling inputs, data, model design, and assumption, and foster the accessibility of planning outputs to key stakeholders.